Okay, so that quick summary, I thought the recorder was on, it wasn't, it's still on, so it didn't turn itself off. Okay, projectile V naught 8 meters per second at 37 degrees. Want to find the maximum value of y? In other words, maximum height that this projectile reaches. Assuming an ideal projectile, you have your R of t function. Okay, I should have the x naught first and the y naught first. I'm going to let them both be 0 anyhow. And this is very straightforward. It's just what we've done before. So here's your R of t function. If R of t is the vector function that describes your path. And just imagine a vector, the tip of this vector traces out your path. Alternatively, you can just say, okay, well, this means that x is this and y is this, because x is what you multiply by I, y is what you multiply by j. So there's your equations for x and y motion. The assumption x naught equals y naught equals 0. Okay, well, we get the components of the initial velocity. It's at 37 degrees at 8 meters per second. Cosine of 37 degrees is very close to 0.8. The sine is very close to 0.6, which is why we use that angle a lot. But whatever the sine and cosine are, you can do the calculation and get the result. So there's no mystery to where those numbers came from. And of course, that then tells us that the y coordinate is v naught y times t. V naught y is 4.8 meters per second, right? Minus gt squared, g being the acceleration of gravity, which I round off to 10 meters per second. So here's the equation for y. If you graph this on a graph of y versus t, this is a quadratic function. It has all the properties of a quadratic function. Just from a little pre-calculus, you can figure out what the vertex of that parabola is. We're going to do it using calculus since we're now in a position to do so. So, right there's your graph. The maximum is going to occur when the slope is 0. Slope is a derivative, so that occurs when the derivative is 0. Some people didn't have any trouble taking the derivative, so we got, this function, derivative of t is 1, so y prime would have a 1 here. And derivative of t squared is 2t, so we're going to have a 2t here. And we work this out, and there's the y prime. We set that equal to 0 and easily solve for t. We find that t is 0.48 seconds, meaning 0.48 seconds after this thing is projected, it's reached its maximum height. Let's start following. Maximum occurs then at 0.48 seconds, so what's the height? Well, you got to do a little more calculation. You know when, you don't know how high it was. But you plug that into the equation of y versus t, 0.48 seconds. Plug into this equation is going to give you the height, and the thing comes out something around 1.15 meters. This is done in my head. I made a mistake. I squared t, then I squared it again, because I forgot that I'd squared it, and came out with 0.3 meters here, but 1.25, or close to it. And I approximated y as 0.5 seconds, so if you do it with 0.48 seconds, these numbers are going to be a little different, okay? Okay, well, that's very straightforward. You just write down the equation of motion, assemble all your information, and there you've got it. Okay, what's the path in space? It's y versus x, right? Well, you know that y, just copying down, is y is this, and x is 6.4 meters per second times t. That's it. From this, I'm going to put a square in that second. See this one, want to do that one. Okay. That's what t is. Now t is just your parameter. We solve for the parameter, now we can plug that back into y, which is going to be 4.8 meters per second times x over 6.4 meters per second. Not going to have units. Never mind, it's got units. Okay. Not thinking clearly. Okay. Minus 5 meters per second squared multiplied by the value of t, which is now x over 6 meters per second, quantity squared. Okay? So it's going to be approximately, this is 3/4, going to be 0.75 x minus 5 over 6.4 is about 0.7, well, it'll be squared, 0.77, so I could say about maybe 0.13 x squared, give or take a couple hundreds. Okay? So now we can do the graph of y versus x. And we could find the point at which this is a maximum. So we've got a new parabola. We've got a